problem 8 of this problem set, and part A of question 8 is asking for the total impedance of this circuit. So our impedance is Z, and it's given by the equation of the square root of the resistance squared plus the reactance of the inductor minus the reactance of a capacitor squared. This value is 0 because there is no capacitor in this circuit. So therefore the equation becomes the square root of the resistance of the resistor squared plus the reactance of the inductor squared. The reactance of the inductor is given by the quantity of the angular frequency times the inductance of the inductor. Since this problem doesn't have any numerical values, that our reactance is just going to be given by omega L. And therefore our impedance is just going to be the square root of the resistance of the resistor squared plus the quantity omega L squared. So part B of this question is asking for the amplitude of current going through this circuit. So we know that the amplitude of the current is going to be the maximum current value, kind of analogous to the maximum voltage value. So we have the equation that is similar to Ohm's law that gives us Vmax equals Imax times the impedance, and therefore we can solve for the amplitude of our current by the amplitude of our voltage over the impedance. Plugging in our impedance from question A, we get that our maximum current is equal to the maximum voltage given by V naught over our impedance.
For part C of this problem, we want to find the amplitude of the voltage across the resistor. The amplitude of this voltage is just going to be the maximum voltage across the resistor, which we have the equation as Vmax is equal to the maximum current times the resistance. In part B, we found the maximum current to be the initial voltage over the square root of the resistance squared plus the reactance of the inductor squared, and then times the resistance. For part D of this problem, we want to find the amplitude of the voltage across the inductor, which again is just going to be the maximum voltage across the inductor. The equation we have for this is the maximum current times the reactance of the inductor. So again, the maximum current is the initial voltage divided by the square root of the reactance squared plus, or the resistor squared plus the reactance of the inductor squared. And then the reactor of the inductor is omega L. For part E of this problem, we want to figure out at what angular frequency are these amplitudes the same for the resistor and the inductor. So we would just set both of these equations equal to each other and solve for omega. Doing this, we find that initial voltage times the resistance is equal to this all cancels, and solving for omega, we find that is equal to the resistance divided by the inductance.
So for part F of this problem, we are looking at how a increased angular frequency will affect the overall voltage in the circuit. So if we claim that our angular frequency is infinity, to see the greatest change, we then will use the equation we found in part B. So for the Vmax, so we have V naught is the angular frequency times the inductance over the impedance. So if we plug infinity in for all the angular frequencies, we will then get
V naught infinity over infinity. So at this point we can cancel out the infinities and we get V naught. So with a greatly increasing angular frequency, our voltage will just be the maximum voltage through the circuit. So in part G of this problem, we are looking at the opposite of part F. So we're looking at a decreasing angular frequency. So in this case, we'll make our angular frequency equal 0 to see what the greatest decrease has an effect on the voltage. So if, again, we will use the same equation that we found in part D. So we'll put our 0 in for the angular frequency. So in this case, we get V max 0 over R. However, because we have a 0 in the numerator, we then will get a voltage of 0. So as the angular frequency decreases to the lowest value it can get, 0, we get 0 voltage through the circuit.